Hello everyone. In this video, we are going to talk about some common errors, mistakes that exist with the print files that you want to either 3D print yourself or send it to somebody else to 3D print it for you. If you can avoid these problems, issues, mistakes, your end product, your 3D printed part would most probably have a lot less issues and look a lot better. What are they? One of the problems is improper tolerance of joints. So if there are parts that go together, they are assembled together, right? The major thing is you make sure they can be assembled. Okay, plastic parts are not similar to the metal parts, that when you have a metal part and the male component is a little bit bigger than the female component, then you can use heat treatment and press fit and create something we call an interference fit, right? Where the two parts hardly separated from each other. In plastic parts, it's not that easy. The plastics do not have as much thermal expansion as metal parts do. So if you make here, let's say this bottom part that needs to go inside the top part a little bit bigger, then it's not so easy to assemble it, okay? And if you apply too much of pressure, these plastic parts will definitely break and will deform. So you need to make sure that in most of the time it is either a clearance fit, so the male part is a little bit slightly smaller than the female part, or you're very close, so maybe with reasonable, without breaking the parts, force, you can do a transition fit, but definitely an interference fit, right? That's not a good idea with plastic parts. So that's number one problem that you see in assemblies. Now, about single parts, one of the major problems you see is infinite edge. I'll discuss items 1 and 4 together. So let me first go through item 3, then I will discuss 1 and 4 because they're close. Item 4 is called an infinite edge, and another way to describe it is edges that are very, very thin, like one layer or below one layer thick. And when you print them, then you're going to see some parts of the edge as missing. The printer could not print it, or there was failure during printing those very, very sharp, thin edges, as you clearly can see here, right? Some parts of the trailing edge of that wing is missing. It was not printed. And here I'm going to show you a demo of that. So here is a wing, right? A simple wing, of course, not super realistic. And I made this trailing edge very, very sharp and very, very narrow at the end, deliberately. So if I go ahead and export this as an STL file and then bring it into my slicer software, see what happens. So here, I bring it in and I print it upright to avoid any support, right? First of all, you see right off the bat, it gives me an error, okay? There are some edges, which are definitely here, that have errors. So if you ever see this, and I'm gonna address all of these issues and all of the things you need to know about Prusa Slicer in a separate video in my next video. But if you see that exclamation mark, it means you have to fix the rest of the errors. There are probably non-manifold edges or some other errors you have to fix. So do not slice right off the bat. Click a left click on this and let it repair those edges. When that goes away, now go ahead and slice. And now see what happens when I look at this guy. So here, this is, okay, this is the skirt, this dark brown one, but let me go to the very base of the part here. So now you clearly can see that what is happening to this edge. First of all, on the first layer, it could get it as sharp as possible, but on the rest of the layers, you clearly see some parts of the trailing edge is missing. And if you look at all of these basically jaggedness, that means this edge is definitely not going to be a clean edge, right? So you clearly see the rest of it is absolutely what? Missing. It's just the very bottom of it that you can get. And I show you the top view, and if I zoom again at this trailing edge, you clearly again can see that there is this area here. You see this line. If you can see that, that is where for the first layer it could print the sharp part of the edge, a little bit of it, not even entire part of what you have in CAD, but for the rest of the layers it couldn't. And now when I switch from the slice mode to the 3D editor mode, see that this edge extends, okay? But when it came to printing it, it has to kind of cut a portion of it off because that was too sharp and too narrow for the printer. Look here. You see, look at the difference that this tip point has with respect to my grid line of the printer bed. And now look here. You clearly see this gap is definitely bigger than what you have here. So this very sharp end of it, this part, from this point to the right, it could not print. And the best it could do is it tried to get closer to it in the first layer, but for the rest of the layer, you definitely have a failure. And even if you try to improve it a little bit, there is still always the chance that you get a very bad edge or some parts of the edge missing, as I said. Call it an infinite edge. So if you want to avoid such a thing, make sure the very tip of very narrow areas like this, you try to cut it, put a chamfer to it or something to avoid that sharp of an edge. So if I want to go back here, right? See, as I said, either you can apply a chamfer or you modify your sketch. So you see clearly my sketch is definitely way too sharp. If I wanted to modify this, I bring a line here in SolidWorks and maybe try to just cut from this part on, right? Draw a vertical line like this, and then trim this rest of it like this. Okay, so now it is definitely a lot better. It's not going to be as sharp as that, and hopefully it can handle it. Again, most probably not so much because this edge that I made still in the very sharp area, right? But if I can show you, maybe I can move it a little bit further to the left. Let's see. Okay. Most probably this is going to ruin my profile. So what I can do is go ahead and bring the line further a little bit more to the left. So maybe something like this. Okay, and then retrim again the rest of it. So make sure that you do not really leave something super sharp behind. Okay, and now if I, you see, that's a lot more reasonable this time, hopefully. Let's go ahead and save it and export it as STL again. Override the previous one and then re-slice it, and you'll see what's going to be the difference. So here I bring it again. If there is an error, again, I make sure I repair it, slice it. And now let's go ahead and check the bottom here. You still see there is a little bit of that left, as you can see. Okay, you absolutely see there is still not an amazing job, but if I look at this guy from the top now, in the slice model and in the 3D model, there should not be a huge difference between them. So you see now they are quite closer to each other, right? So there is not a huge difference between those two gaps that I showed you. And again, if it's still too sharp, I would trim it a little bit further back, right? So just go back here and redo that. Here we go. So I trimmed it a little bit further, and now you clearly can see that I don't have any discrepancy at the bottom layer, right? And the edges, the end of the layers seem to be very well aligned with each other, right? And if I look at it again from the top, there should be really no difference anywhere between the layers and then between 3D model and the layers. Okay, so make sure to avoid infinite edges. Now, another important thing is the dimensions of the part. Remember that, as we discussed in our previous video about the 3D printing parameters, we have a layer height and we have the nozzle diameter, and those will determine the resolutions of X, Y, and Z plane. So if your nozzle is 0.4 mil, means the minimal thickness you can achieve on the XY plane, on any flat plane, on any layer is 0.4 mil. And if the layer height that you choose is 0.2 mil, means that's the best you can get, right? So you have to make sure the overall height of the part is a multiple of 0.2 mil, an integer multiple, and any dimension in the X and Y is an integer multiple of 0.4 mil, right? So let's say, as I said, let's say you have a simple cube, right? If you have a simple cube like this that you want to print upright, then this width has to be an integer multiple like n times 0.4 mil. And this depth also has to be, again, n times 0.4 mil. Now, you might not be the same n, so you might call them n1 and n2, because along xy plane, where the w and d fit, there is a 0.4 millimeter thickness or diameter of the molten plastic. And then the z, if you call it height, this height should be another integer multiple like n3 times the layer thickness. If the layer thickness is 0.2, then let's say it should be like that. And why is it important? Because sometimes I see like the students make parts and they submit it to our lab for printing, but they make this width to be, let's say what? They make it to be like 12.1 mil, and they make like this one to be, let's say, 5.3 mil. Well, the problem is this. This 5.3 is not an integer multiple of 0.4. The same thing for 12.1. So what's going to happen is the printer has to skip a layer or add a layer, right? And it does it by rounding. So definitely for this case, it would definitely round this to 12, the closest multiple, integer multiple of 0.4 to that number. And for this, if it rounds it, then it rounds it to the closest, again, multiple of 0.4, which is like 5.2 for this case. Okay, so the dimension that you will get at the end of the day for that W and D that you design is going to be this one. Going to be 12 by 5.2, not 12.1 by 5.3. In the CAD software, you can put whatever dimension that you want. 3D printer cannot give you in the real world. The same thing with the height. You might say, hey, I want this height to be, let's say, 6.1 mil height. But 6.1 is not an integer multiple of 0.2. So this one is probably rounded to 6. Or maybe it goes up because it's between them. Maybe it goes to 6.2. Right? So you either get it a little bit taller or a little bit shorter. So if you get it to not perfectly match what you want, and if the dimensions and tolerances are tight, make sure your initial dimensions match the capabilities of your printer. Okay? And here I'm going to show you that in an example. So here I'm going to make this guy, it's a little bit too tall. Let me reduce the height of this. So I make the height of this maybe what? 2.1 mil, right? So I make it something short like this, flat. and then I'm going to save it again as STL, and then here I'm going to import that flat piece again that you can see now, and now I'm gonna slice it, and I expect the overall height to be what? Let me change this to 0.2, which is the layer height that I said you can normally have on a Prusa, although you can go further down. But here I did that, right? And what's going to happen here? You see clearly the Z direction, the height of the imported part is 2.1. Now, will you get 2.1 in the real world? Let's go ahead and count the layers. So we count each layer that we'll get and multiply it by 0.2, right? So starting from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you will get 10 layers. And 10 layers times 0.2 is what? 2 mil, not 2.1. You see? You cannot get half a layer. You either get no layer or 1 layer extra. So definitely that's not a good idea to go with the dimension of 2.1. And the same thing happens again, as I said, if you choose the other two dimensions not to be an integer multiple of 0.4. So make sure that you choose your dimensions right. One other thing that many people choose and they want to print, which I mentioned in my previous video, is parts that are shelled with very, very thin walls, like as thin as 1 layer. That's absolutely not a good idea to print something with 1 layer wall thickness to be printed. So you might here have this part and then go ahead and shell it with 1 layer, so like 0.4 mil, right? So get it to something like this. Here I just made it a little bit also taller and exported it as STL, and let's go ahead to the slicer software and try to slice this very thin-walled object, see if we can get anything. So here is the part, that's the STL of it, right? And as I said, I made the walls a little bit taller. Let's go ahead and slice, and if you do, you're gonna see something interesting. First of all, it cannot even get the walls for you. Although they were 0.4 mil, but in the software setting, if you go to your print setting and look under advanced, you see that the default extrusion width is actually a little bit more than 0.4. Okay, so by adjusting the speed of the print, you can even change that 0.4 to something a little bit more or a little bit less. So because this one is 0.45, that means you are not even getting that 1 layer. So I have to go back here and change my shell to maybe something like 0.45 or 0.5 or something, right? Make it a little bit thicker, so hopefully it can give me 1 layer, right? And even if it does, as I said, and it gets to slice it, it's absolutely not a good idea to print something that thin. So let's see here, you see? Now that you pass that threshold, it can get you 1 layer, and you clearly can see it's just 1 layer, and look, that's another thing that you might get. Artifacts like this, look at that. So it could not slice it properly, and in areas with a sudden change in the curvature like this, it cannot even go continuously print that curvature for you. And then don't be surprised if that 1 layer wall that you have is not even complete like this. Okay, so as I said, by no means go for designs like this. Make sure the shell thickness is at least minimal 2 layers, minimal. Okay, so definitely if you want something here, 2 times 0.45, you want 0.9. That's like a minimal thing that you want to avoid artifacts like that. And here, that's what you can see. I change it to 2 layers. So now at least you're not going to get discontinuities in the print, and hopefully it lasts a little bit more, although definitely not really some wall that you want to apply any force or anything to, but at least it can print it. So keep that thin walls in the mind. A couple of other things. One is small slopes. So if the part that you have has small slopes in it, in the Z direction, remember your printer goes up by 0.2 mil or something like that in each layer. And if the slope you are trying to print is very mild slope, it's just a few degrees or so, then you are going to get something like this. Let me make it bigger. You see this kind of step type behavior. You see the discontinuities, and this is called stepping. So here, as you can see, there are two problems with this wing. One is definitely you see the infinite edge, and you also see the stepping. So that's definitely not a good design for 3D printing. That's definitely a bad file that you can see over there. Here to show you a brief demo of what's going to happen in the software is, here I made this kind of almost flat part, but a very gentle slope here. It's just 2 degrees. And this small draft angle that I provided, now I'm going to get it into my software, right? And here I resized it to fit the print bed. And then if I try to slice it, which I already did, you clearly can, if you look from the side, you clearly see this stepping behavior, right? You can see it right now very well. Let me see if I can show you from a good direction here, right? You clearly see these jumps, this stepping behavior, okay? So it's gonna be something like a xylophone or so. So that's the problem with small slopes that you have to keep in mind. Your printer cannot achieve all of that. If you want to get it a little bit better, you definitely need to bring down your layer height. So if I go to ultra detail, then probably I get it a lot nicer. Of course, it's gonna mean a lot more printing time, but at least it can give me a lot less stepping effect, just like what you saw. So you see here is trying to slice it with 4 times smaller layer height, and hopefully the top surface is not going to be as bad as what you just saw. There we go. Seems like it is sliced. Now if I look at it from the side, now you still see that if you zoom a ton, but definitely you have to zoom a ton. If you look at it from the top, those layers are so smaller that the stepping effect is really much less. Okay, but if you have the bigger slope, you're not going to see as big as effect as you just saw with the smaller slope. So here I changed that draft angle to 30 degrees instead of 2 degrees, and I brought it back into Slicer software, and I used the same layer height of 0.2, not the ultra thin of 0.05. And you see the stepping effect is much more tolerable compared to what you had at 2 degrees, right? So definitely smaller slopes are not a good idea, especially to be used with a layer height that is not ultra thin. Good. So the last item in my list for tonight is the resolution when you export your CAD model. So the CAD models that you have are typically a parametric model like this. So if you have a sphere, right, when you export it as a mesh file like STL, you have to use a good resolution of that mesh file, because if you don't, then the surface that is approximated of the parametric model in the STL is going to be really rough. And when the model that you exported, the STL, is rough, the software that is doing the slicing cannot do magic. It can never give you a good print. You are never going to get a good print if the STL you import is a bad STL. So to show you the effect of the STL resolution or any print file resolution, here is a part that is a little bit more complicated than the wing, right? And I'm going to 3D print this, right? This coordinate frame. And I'm going to basically save this as STL, right? So I go to STL and then I save it. And then I call a version coarse and a version fine. But where is fine and coarse? How do you change the resolution of STL files in SolidWorks? So when you choose your file type to be STL, you go to options. And then in the options, you can have coarse mesh, you can have fine mesh, and you can have custom. So here I go with the fine mesh, right? Using a bunch of points and call, as I said, one version fine access, right? You clearly see it uses 6600 triangles and the size of the file is about 331 megabytes or something like that. Not exactly because each megabyte is 1024 kilobytes, not exactly 1,000. But this is the fine mesh. And now again, I go and resave this as STL, but this time as a coarse mesh. Okay, so you'll see when I bring them into the software, you're gonna see some big differences. So this is coarse mesh. Now here, you see, now it is only 2,000 triangles instead of 6,600, and the file is about a third of the volume of what it used to be. The mesh is coarser. I can even make it coarser if I want to. Still, it's not like crazy coarse, but much coarser than last time. And now let's go to the slicer software. So here are both of them imported. This is the finer mesh. Look at the surface. And this is the coarse mesh. Look how bad it is already without even you trying to print, right? And this coarseness, or look at the shaft here, right? Look at the cross section of it and look at the cross section of this one. It's much finer. And when you slice that, that is going to show itself even more. So clearly you see there are some empty layers that are detected, right? So it is outside the print area. Seems like it's not happy. And if I print it with the fine mesh, you see, there is no problem. It doesn't even pick on me. I can absolutely print the fine mesh, no problem. It can do it. But when I import the coarse mesh, look here, and trying to slice it, you see, it gives me an error. There are some problems, although it did not really find an error in the beginning to begin with, but now it cannot even print it. The mesh was too coarse that it cannot print some of those jagged areas. So a coarse mesh is absolutely not recommended. Sometimes it cannot even print it if the geometry is complex and have sharp edges, abrupt discontinuities. And even if it can, it's going to give you a very bad surface. So changing the resolution of STL to fine mesh is definitely recommended. This was for SolidWorks, and some of you might use CATIA and say, well, how would you do that in CATIA? How would you change the resolution of the STL file in CATIA? Well, in CATIA it's a little bit different. So in CATIA, let's say if I have this part and I want to export this for rapid prototyping, in CATIA, if you want, if you go to File, Save As, right, and you want to save this guy as STL, it does not give you any option here, like SolidWorks, to change the STL mesh. What you need to do is to go to Tools and Options, and then go to Display. Under General, you go to Display, go to Performance, and then here you can change these factors of 2 and 3D accuracy. Okay, if you make these numbers bigger, you're going to get a rougher mesh. If you make them smaller, you're going to get a finer mesh, right? So you clearly see if I go up here, the circle that I have is now definitely converted to, it's not, you never get a perfect circle anywhere in a CAD software. They are always polygons, but the number of size of the polygon will determine the amount of surface quality, right? So instead of 0.02, if I use 0.5, you see definitely I can see the jaggedness, and the same thing here, right? If you bump this number up, you're definitely going to get a rough mesh, correct? So let me also bump this up to 0.5. So I okay that, and then I will save this as STL, and maybe I call it part number 3 underscore coarse, right? That's a coarse mesh file. Save it, then go back and put those numbers back to what they were. I guess they were 0.02 each, right? So make it very, very fine mesh. Okay that, and now again I'm going to save that as STL, and I'm going to call it part 3 fine, right? And save it as STL again. Now let's go ahead and add them to the slicer software. And here are those two files. You see big differences now, right? See huge differences in the surface quality. And of course, when you slice it, you are going to get different slices too, right? The software, as I said, cannot repair the rough surface for you. It's gonna even make it, the 3D printing, make it rougher. So do not bring a file with very coarse mesh quality. Look at that, right? You clearly can see, even if you go down, you see the huge difference in terms of surface quality, right? You see the polygon very visibly here. Here is again a polygon, but with too many sides that you can barely see, right? Now, and I know that it makes a big difference in terms of the volume. If you look here, this coarse file is like 44, 45 kilobytes, while the fine mesh is like 223 kilobytes, like 4 times bigger, but still none of those numbers is such a huge number for the storages these days and for what a 3D printing software can handle. Okay, I have printed for parts that were like several hundred meg, close to a gig STLs, and Prusa could really slice them, and I could print them. Okay, so do not bring a bad STL file inside whatsoever. Hopefully these 6 very important topics was useful to you and guide you in a direction that if you try to print something yourself or ask somebody to print it for you, you observe these important rules and get a much, much finer, better end product. So thank you so much for your attention. See you in my next video.